Let me ask you something. Have you ever stepped outside on a clear night, looked up, and felt it, that quiet, almost unsettling feeling that you are incredibly, impossibly small? That the sky above you stretches so far in every direction that your mind genuinely cannot hold the scale of it? Most people push that feeling away. They go back inside, they make dinner, they scroll their phone. But some people, scientists, dreamers, engineers who eat lunch at their desks and go home thinking about orbital mechanics, those people lean into that feeling. They chase it. And the things they've found while chasing it are so much stranger, so much more beautiful, and so much more terrifying than anything you could dream up on your own. That's what today is about. We're going to travel. Not a little. We're going to move from the edge of our solar system to the nearest star, from the frozen south pole of our own moon to the surface of Mars, from the storms raging at Saturn's north pole to the question that keeps astronomers awake at night: is anyone else out there? We're going to cover things that genuinely happened, discoveries that were made within the last few years, that rewrote textbooks and forced scientists to go back and rethink assumptions they'd held for decades. Some of what we'll talk about sounds like science fiction. It is not science fiction. It happened. It's happening right now. And if you stay with me to the end, I promise you will look at the night sky a little differently. So let's start at the destination. There is a star, about 4.25 light years from our sun. That sounds like a manageable number until you do the math. 4 light years is roughly 25 trillion miles. 25 trillion. If you drove at highway speed for your entire life, you would cover a fraction of that distance. The fastest spacecraft humanity has ever built, Voyager 1, which launched in 1977 and has been flying ever since, would take roughly 75,000 years to cross that distance. And yet, in 2016, astronomers discovered that a planet is orbiting that star, a planet called Proxima Centauri b, a planet that sits inside what scientists call the habitable zone, the region around a star where temperatures could allow liquid water to exist on a surface. The closest potentially habitable world beyond our solar system is 4 light years away. It might as well be next door compared to how far other candidate planets are. And people are already talking seriously about how to get there, not in 75,000 years, in 20. That's not a typo. There is a project, a real, funded, international scientific project called Breakthrough Starshot, and its goal is to send a probe to the Alpha Centauri system within our lifetimes. The way they plan to do it is genuinely one of the most audacious things the human mind has ever conceived. They want to build an array of lasers on the ground, 100 gigawatts of focused optical power, which is roughly 100 times the capacity of the world's largest battery, and aim all of that light at a sail. Not a big sail, a tiny one. A wafer-thin, highly reflective sheet no bigger than a postage stamp attached to a spacecraft the size of a microchip. The light from those lasers would push on that sail the way wind pushes on a ship's sails, except instead of wind we're talking about photons, and instead of a gentle breeze we're talking about 100 million laser beams focused into a single coherent stream. The result, in theory, is acceleration to 20% of the speed of light. At that speed, Alpha Centauri is a 20-year journey. Now here's the part where most people expect me to pivot and explain why this will never work. That's not what I'm going to do. Because the challenges are real. You need to synchronize 100 million lasers to hit a centimeter-wide target, and the engineering required for that is genuinely staggering. But those are engineering problems. They're hard. They're not impossible. Researchers from the Australian National University have already proposed using a laser guide satellite to maintain accurate targeting throughout the voyage. The materials science, the optics, the computing power, all of these are advancing. The question isn't whether it's physically possible. It is. The question is whether we can build the thing. But let's take a step back, because Breakthrough Starshot is the flashy headline. The real story of humanity's ambition toward the stars is a long one, and it starts earlier. It starts in 1961, when Yuri Gagarin strapped himself into a rocket and became the first human being to orbit the Earth. Think about what that moment meant. 40 years before that, the airplane was barely a decade old, and suddenly a man was orbiting the planet. 8 years after Gagarin, Neil Armstrong was standing on the moon. We moved so fast in those decades that it still doesn't feel real. Armstrong and Aldrin landing in 1969 wasn't just a flag in the dirt, it was proof of concept. It was humanity demonstrating to itself, in the most visceral possible way, that we could reach other celestial bodies. that the universe was not permanently locked behind a glass window. Then came the Voyager missions in the 1970s, which gave us our first real look at the outer planets, and eventually slipped through the edge of our solar system into interstellar space, where they still drift today, carrying golden records filled with the sounds of Earth, music, greetings in dozens of languages, the sound of waves, laughter, a child's cry, messages in a bottle thrown into an ocean with no shore in sight. The thread from Gagarin to Voyager to breakthrough Starshot is a single unbroken thread of human refusal to accept that the universe is beyond reach, and that refusal has real consequences. It produced ion engines, propulsion systems used on missions like NASA's Dawn spacecraft that use electricity to accelerate charged particles, generating thrust with an efficiency that chemical rockets can't match. It produced gravity assists, the slingshot maneuver that New Horizons used at Jupiter to fling itself toward Pluto, covering more than 3 billion miles in just 9 years. And even then, arriving at Pluto at a speed that would take it roughly 80,000 years to reach Alpha Centauri. Scale, again. The universe is genuinely that big. There are other concepts in the pipeline that sound even wilder than light sails. Nuclear pulse propulsion, the idea of detonating a series of nuclear bombs behind a spacecraft to generate thrust, was actually developed in the late 1950s under a program called Project Orion. The calculations showed that such a spacecraft could theoretically reach 10% of the speed of light. That's still a 40-year journey to Alpha Centauri, but it's a journey you could plan within a single human lifetime. Then there's antimatter propulsion, which is perhaps the most powerful concept of all. When antimatter meets matter, both annihilate each other and release an almost incomprehensible amount of energy. An antimatter engine could, in theory, push a spacecraft to a significant fraction of light speed. The problem is that antimatter is currently produced in quantities so small that you'd need decades of output from the world's particle accelerators just to fuel a matchbox. We're talking about the most expensive substance ever created, measured in billions of dollars per gram. But the research continues, because if you ever crack the production problem, the payoff is essentially unlimited. And then there's warp drive. Yes, I'm going there. Not Star Trek warp drive, not pure science fiction, a theoretical framework proposed by physicist Miguel Alcubierre in 1994, grounded in Einstein's general theory of relativity, that suggests it might be physically possible to compress space in front of a spacecraft and expand it behind, effectively moving the craft faster than light without technically violating the laws of physics. The ship doesn't move through space. The space itself moves around it. The challenges are enormous. It requires exotic matter with negative energy density, which has never been observed. But the physics doesn't flatly forbid it. It's a legitimate area of theoretical research, and that distinction matters. The reason all of this matters, not just as beautiful science, but as urgent human business, is that in 2016, astronomers confirmed that Proxima Centauri b is real. They found it using the radial velocity method, which detects the tiny wobble that a planet's gravity induces in its host star as it orbits. The wobble is almost impossibly subtle, a star shifting back and forth by a few meters per second across 4 light-years of space. But we can measure it, and what we found is a planet roughly the size of Earth, orbiting at a distance that puts it in the habitable zone of Proxima Centauri. That doesn't mean it's comfortable. Proxima Centauri is a red dwarf, and red dwarfs are violent. They throw out stellar flares that could strip the atmosphere from a close orbiting planet. Whether Proxima b has an atmosphere, and if so, what's in it, we genuinely don't know yet, but it's there. The nearest potentially habitable planet is 4 light-years away. That changes things. Now, whether we're sending a microchip on a laser sail or a crewed generation ship carrying 1,000 people across interstellar space, the fundamental question behind all of it is the same. What are we looking for? Is there something out there worth the journey? Is there life? Is there someone home? That question has been asked for as long as human beings have looked at the stars. But only in the last few decades have we had the technology to actually try to answer it. And the way we're trying is more sophisticated, more beautiful, and more strange than most people know. There are 2 parallel tracks in the search for life beyond Earth. The first is the search for biosignatures, chemical fingerprints that only life produces. The second is the search for technosignatures, signals and structures that only technology produces. Think about that distinction for a moment. Biosignatures could be the oxygen in a planet's atmosphere, built up over billions of years by photosynthetic organisms the way Earth's oxygen was built up by ancient cyanobacteria. Technosignatures could be a radio transmission, or a megastructure, something like a Dyson sphere, a theoretical construct that wraps around a star to harvest its energy that no natural process could create. One track is looking for any life. The other track is looking specifically for civilizations. The James Webb Space Telescope is the most powerful instrument ever built for the first track. JWST uses a technique called transmission spectroscopy, which works like this. When a planet passes in front of its star, a tiny fraction of the star's light passes through the planet's atmosphere. Different molecules absorb different wavelengths of light, so by analyzing the spectrum of that starlight after it's passed through the atmosphere, you can read the chemical composition of the atmosphere itself, like a fingerprint. JWST is sensitive enough to detect water vapor, carbon dioxide, methane, oxygen, ozone, any of which, in the right combination, would be an extraordinary finding. Scientists are particularly watching for the simultaneous presence of methane and carbon dioxide, which can't both exist in large quantities at the same time without constantly being replenished, suggesting ongoing biological or geological processes. The presence of phosphine in a planet's atmosphere would be another major flag. On Earth, phosphine is associated with anaerobic ecosystems, with biological activity in oxygen-free environments. Finding it on another planet where no known non-biological process could produce it in significant quantities would be an extraordinary signal. But biosignatures have their limitations. They can tell you that something is alive somewhere. They can't tell you whether it's intelligent. For that, you need to listen differently. Breakthrough Listen is the largest and most comprehensive SETI project ever undertaken. Launched in 2016 with $100 million in private funding, it uses some of the most powerful radio telescopes on Earth, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to scan the sky for narrowband radio signals. Narrowband signals are the key phrase. Natural cosmic processes produce broad-spectrum radiation. A narrowband signal, concentrated into a single frequency the way a radio station concentrates its broadcast, is something that nature essentially never does on its own. Finding one would be extraordinary. So far, Breakthrough Listen has found nothing conclusive. Every interesting signal, when followed up, has turned out to have a terrestrial source or a natural explanation. But the search has barely begun. Our galaxy contains roughly 100 billion stars, and we've surveyed a tiny fraction of them in any serious way. The challenges are real. Signals dilute across light years, becoming fainter with distance. Radio interference from Earth's own civilization creates a constant background noise that researchers have to filter out. Distinguishing a genuine extraterrestrial signal from that noise is like trying to hear a whisper at a rock concert. In 2023, an astronomer named Carmen Choza and her team took one of the boldest approaches yet. Instead of searching individual stars, they turned their attention to entire galaxies. Using the Green Bank Telescope, they spent 5 years observing the centers of 97 nearby galaxies, searching for narrowband Doppler drift signals, the kind of signature you'd expect from a transmitter moving relative to you. The logic is elegant. If a civilization has advanced enough to harness the energy of an entire star, what physicist Nikolai Kardashev called a Type II civilization, their transmissions might be powerful enough to reach us from millions of light years away. They would be generating signals on a scale that dwarfs anything we can imagine. Choza's team found over 600,000 candidate signals in their initial scan. After extensive filtering, that number was narrowed to about 1,500 events of particular interest. And then, after exhaustive review, all 1,500 were attributed to terrestrial interference or natural cosmic phenomena. Disappointing on the surface, yes, but the methodology they developed, especially the on-source, off-source cadence pattern that distinguishes real astronomical signals from Earth-based noise, represents a genuine advance. And the data they collected is being reanalyzed now using machine learning, which can find patterns that human eyes miss. The search is not over. It's barely started. The most interesting thing about the Fermi paradox, the question of why, given the age and size of the universe, we haven't heard from anyone yet, is not that it has no answer. It's that there are so many possible answers. Maybe life is genuinely rare. Maybe intelligence is even rarer. Maybe civilizations inevitably destroy themselves before they develop the technology to reach across interstellar distances. Maybe the signals are there and we just haven't been listening to the right frequency. The honest answer is that we don't know. What we do know is that we have been seriously looking for about 60 years, with technology that would look like stone tools to any civilization even 1,000 years ahead of us. We are at the very beginning of this search. Now let's talk about something closer to home. Something we once thought we understood, and then discovered we'd been fundamentally wrong about for decades. Let's talk about Neptune. Most people, if you ask them, will tell you that Neptune is deep blue, vivid electric blue, the color of a tropical ocean at noon. That image is so widespread, so embedded in every textbook and poster and space documentary, that most people have never thought to question it. Here's the thing, it was wrong, not slightly wrong, not a matter of shade or tone. The deep blue color of Neptune, as it appeared in virtually every image you've ever seen, was an artifact of how those images were processed. When Voyager 2 flew past Neptune in 1989, the only spacecraft to ever do so, it captured images in multiple wavelengths that scientists combined into a composite color image. That image was enhanced and processed to emphasize certain features and make them more visually distinct. The result was a beautiful picture that became the definitive image of Neptune for over 3 decades. But it wasn't an accurate representation of what Neptune actually looks like to human eyes. In 2023, a team led by Patrick Irwin at Oxford University set out to study something apparently unrelated: the seasonal color changes in Uranus's atmosphere. In doing so, they ended up reanalyzing Neptune data from the Hubble Space Telescope alongside decades of ground-based observations. What they found was revelatory. Neptune's true color is not the deep, vivid blue of every poster you've ever seen. It's more of a pale greenish blue, noticeably similar to Uranus, which, you may recall, everyone has always described as distinctly different in color from Neptune. They're not as different as we thought. We were looking at a corrected photograph and thinking it was reality for 30 years. This matters beyond aesthetics. The color of a planet's atmosphere reflects its composition, the way methane and other gases absorb and scatter light. Getting the color right means getting the chemistry right. And Neptune's chemistry is worth understanding, because its atmosphere is doing things that genuinely puzzle planetary scientists. The fastest winds in the solar system blow on Neptune, over 1,000 miles per hour. For context, the most destructive hurricanes on Earth top out around 200. Neptune's storms are driven by winds 5 times faster than that, and the source of all that energy is a mystery, because Neptune receives very little heat from the sun at its vast distance. Something in Neptune's interior is generating energy that drives weather systems of extraordinary violence, and we don't fully understand what it is. There are also hot spots in Neptune's atmosphere, localized regions where temperatures spike to around 750 degrees Kelvin, on a planet whose average temperature is -200 degrees Celsius. The heat source for these spots is unknown, though theories point to internal processes, possibly magnetic reconnection in plasma layers or deep auroral activity. These are not peripheral puzzles. They're fundamental questions about how giant planet atmospheres work, and answering them helps us understand similar worlds orbiting distant stars. Neptune's moon Triton deserves its own conversation because Triton is not like other moons. Most large moons in our solar system orbit in the same direction their planet rotates, a natural consequence of formation, everything in a protoplanetary disk spinning the same way. Triton orbits Neptune backward, retrograde. That single fact tells us an enormous amount about its history. Triton was not formed alongside Neptune. It was captured. Some long ago close encounter resulted in a world that had been wandering the outer solar system becoming locked in orbit around Neptune, doomed eventually to spiral inward and be torn apart by tidal forces, though that won't happen for millions of years. In the meantime, Triton is geologically active. Its surface is covered in nitrogen ice, and dark streaks running across it indicate active geysers erupting nitrogen gas into its thin atmosphere. The Very Large Telescope has shown that Triton's southern hemisphere is experiencing summer right now, and summer on Triton lasts over 40 years because Neptune takes 165 Earth years to orbit the Sun. During this extended summer, nitrogen and methane ices sublimate and thicken the atmosphere in ways that scientists are still working to fully model. And then in 2022, the James Webb Space Telescope captured the clearest image of Neptune's ring system in over 30 years, the best view since Voyager 2's flyby. Some of those rings had barely been detected since 1989. In infrared light, Neptune itself doesn't appear blue at all. It appears as a pale, luminous white sphere, because methane gas strongly absorbs infrared light, and the high-altitude methane ice clouds reflect sunlight back before it can be absorbed. It's a completely different face of the same planet. Everything we thought we knew about what Neptune looks like turned out to be a story we told ourselves. From Neptune, let's come much closer to home. In August 2023, India's Chandrayaan-3 spacecraft touched down near the lunar South Pole, the first spacecraft in history to successfully land in that region, and began returning data that has already changed our understanding of the Moon. The South Pole of the Moon is unlike anywhere else we've landed. It's a landscape of permanent shadow, of craters that haven't seen sunlight in billions of years, of temperatures that can plunge to -382 degrees Fahrenheit. Some of those shadowed craters are literally colder than Pluto. Scientists have long theorized that water ice could be hiding there, deposited by comet impacts over billions of years and preserved by permanent darkness. Water ice on the Moon isn't just an academic curiosity, it's rocket fuel. It's drinking water. It's the difference between a moon mission that requires carrying everything from Earth and a moon mission that can sustain itself and serve as a gateway for deeper space travel. Chandrayaan-3 didn't find direct evidence of water ice on the surface layer, but the absence of a definitive finding is not a negative. One theory is that the ice is trapped deeper beneath the surface, shielded by the insulating properties of the regolith. Another is that it's distributed unevenly, concentrated in specific shadowed regions the rover didn't directly traverse. The next mission, LUPEX, a joint Indian-Japanese mission planned for no earlier than 2026, will carry a drill capable of sampling material from 1.5 meters below the surface. That's where the answers may be. What Chandrayaan-3 did find was remarkable in other ways. Its temperature probe measured something stunning. At the lunar surface during the day, temperatures reached around 140 degrees Fahrenheit. Just 8 centimeters deeper, they dropped to around 14 degrees. The regolith is an extraordinary thermal insulator, creating a temperature gradient that drops over 100 degrees across a distance shorter than the length of your hand. For future lunar habitats, that's significant. Structures built beneath the surface would be insulated from the brutal thermal swings of the lunar day-night cycle, which spans 14 Earth days each. That regolith layer might be the difference between a habitat that's survivable and one that isn't. Then Chandrayaan-3 detected what appears to be a moonquake, the first such observation since the Apollo seismometers fell silent in the 1970s. Moonquakes are caused differently from earthquakes. The Moon has no tectonic plates. Its quakes can be triggered by meteoroid impacts, by Earth's gravitational tidal forces pulling on the lunar crust, or by the extreme thermal expansion and contraction that happens as the surface swings between scorching heat and freezing cold. What makes them scientifically fascinating is that they propagate differently from earthquakes. The Moon's rigid, dry interior allows seismic waves to travel farther and last longer, sometimes up to an hour. Analyzing those waves tells you about the Moon's internal structure the same way a sonogram tells you about the interior of a body. And then there's the elemental composition. Chandrayaan-3's LIBS instrument, laser-induced breakdown spectroscopy, which vaporizes tiny samples of surface material with a high-energy laser and reads the resulting light to determine composition, made the first ever in-situ measurements of the lunar South Pole's surface chemistry. It detected sulfur, aluminum, calcium, iron, chromium, titanium, silicon, oxygen. Sulfur is particularly interesting because on Earth it's often associated with volcanic activity, raising questions about the Moon's volcanic history. It also adds a layer to the water ice question. Sulfur compounds may be co-deposited with water ice in the permanently shadowed craters. The search for hydrogen, a key component in the water question, continues. India's role in lunar exploration has shifted from participant to pioneer, and the roadmap ahead, LUPEX in 2026, a sample return mission with Chandrayaan-4 by 2028, is building toward a future where the Moon isn't a destination but a launch pad. Let me take you somewhere that deserves its own chapter in the story of what we might one day call home, even if we've never set foot there. Kepler-22b. In 2011, NASA's Kepler Space Telescope announced the confirmation of a planet orbiting a star about 600 light-years from Earth. What earned this planet the extraordinary attention it received is not simply that it exists. Thousands of exoplanets have been confirmed since Kepler began its work. What makes Kepler-22b special is where it sits, right in the middle of the habitable zone of its star, not at the edge, not in the theoretical margins, squarely in the region where temperatures could allow liquid water to exist on a surface. The star it orbits, Kepler-22, is slightly smaller and cooler than our Sun, but fundamentally similar. The planet itself is about 2.4 times the radius of Earth. We don't know if it's rocky or gassy. We don't know its density. We don't know its composition. If it has a rocky surface with an Earth-like atmosphere, its equilibrium temperature is estimated at around 22 degrees Celsius, roughly 72 degrees Fahrenheit. Comfortable, t-shirt weather. If it has a thick, Venus-like carbon dioxide atmosphere, that same incoming solar radiation could trigger a runaway greenhouse effect and push surface temperatures to nearly 500 degrees Celsius, hot enough to melt lead. The difference between paradise and hell on this world depends entirely on what we can't yet see. The method that found Kepler-22b is elegantly simple in concept. When a planet passes between its star and our line of sight, it blocks a tiny fraction of the star's light, causing a measurable dip in brightness. The Kepler photometer detected a dimming of Kepler-22's light, so small it's described as roughly equivalent to standing across a room from a searchlight and detecting the dimming caused by a dust particle passing in front of it. That's how sensitive this technology is. That's how much effort goes into finding these worlds. And the transit method gives us more than just the planet's size. By carefully measuring how the dip in stellar brightness changes as the planet's atmosphere filters starlight during transit, we can, in principle, read the chemical composition of that atmosphere. For Kepler-22b, at 600 light-years, this is at the very edge of what JWST can do. Difficult but not impossible. And as its observing time accumulates, more distant and more Earth-like worlds are coming into range. The infrastructure being built to study these worlds is itself extraordinary. JWST is operational. The extremely large telescope, when completed on a mountain in Chile's Atacama Desert, it will be the largest optical telescope in human history, with a mirror nearly 40 meters across, is under construction. Future proposed missions like HabEx and LUVOIR are designed to directly image Earth-like planets around nearby stars and search for atmospheric biosignatures with a sensitivity that makes today's instruments look like binoculars. We are building the tools to answer the question. The answer is coming, but let's come back inside the solar system, because we need to talk about a place with more immediate relevance to the future of humanity than any distant exoplanet, a place where humans are planning to go within the next decade. Mars, the fourth planet from the Sun. Average temperature minus 60 degrees Celsius. Atmospheric pressure less than 1% of Earth's. No magnetic field to shield the surface from radiation. No liquid water on the surface. And yet, ancient river valleys, dried lake beds, mineral deposits that could only have formed in the presence of water, a polar ice cap. Evidence of ancient volcanic activity on a scale that dwarfs anything Earth has ever seen, and a growing body of evidence that this dead world was once, billions of years ago, startlingly similar to Earth. Let's start with what Mars looks like today. When Curiosity and Perseverance send images back from the surface, they show a landscape that's eerie in its familiarity. Rocks, hills, valleys, a sky. Then you look at the sky and it's the wrong color, not blue, butterscotch at midday. And at sunset it turns blue. That blue sunset happens because iron-rich dust particles in the Martian atmosphere scatter sunlight differently from Earth's nitrogen-oxygen mix. On Mars, red wavelengths scatter out, leaving blue light to dominate the horizon at dusk. It's one of those details that makes Mars feel simultaneously like home and like something profoundly alien. The Martian atmosphere also produces a faint green glow at night, recently captured by NASA's Mars Express orbiter. During the day, sunlight breaks down carbon dioxide molecules in the upper atmosphere through photodissociation. At night, the resulting oxygen atoms recombine and emit a faint luminescence, the same airglow phenomenon visible from Earth's orbit, but on Mars it's particularly pronounced and concentrated in narrow altitude bands. Then there's the brain terrain, vast regions of the Martian mid-latitudes where the landscape looks, from orbit, almost disturbingly like the surface of a brain. Complex patterns of ridges and channels that wander and interweave in ways that mirror the folds of a cerebral cortex. The current best explanation involves sublimation, the conversion of underground ice directly into vapor, creating these patterns as ice erodes unevenly beneath the surface. But the exact process is still debated, and the scale, stretching across hundreds of square miles, is remarkable. The evidence that Mars was once wet is overwhelming and keeps getting stronger. The Curiosity rover discovered mud cracks in ancient sedimentary rock that closely resemble the dried polygonal patterns that form on Earth when standing water evaporates. The sulfate minerals in those formations indicate that water interacted with Martian soil over extended periods. Ancient outflow channels visible from orbit are enormous, wide enough and deep enough that the flows creating them would make Earth's largest rivers look like streams. There are ancient delta formations where rivers entered lakes. There are sedimentary layers telling of water deposition over thousands of years. And in one of the more surprising recent findings, radar surveys have revealed water ice not just at the poles but at equatorial latitudes, buried beneath the surface in regions where temperatures and pressures would never allow it to exist on the surface today. This changes the picture of Mars's climate history significantly, suggesting multiple epochs of wildly different conditions, some perhaps far more amenable to life than today's frozen landscape. The search for biosignatures on Mars hasn't produced conclusive results, but the Perseverance rover is collecting rock samples from what may be the most promising location we've ever identified, the Jezero crater, an ancient lakebed and river delta. The rocks being sampled contain organic compounds, not proof of life because organic chemistry can happen without biology, but consistent with the kind of environment where life could have flourished. Those samples are being cached on the Martian surface awaiting a sample return mission, currently planned but facing significant challenges, with cost estimates exceeding $10 billion and complexity rivaling any mission ever attempted. Mars is not geologically dead either. The InSight lander, before its mission ended, detected what appears to be the largest Marsquake ever recorded, a magnitude 4.7 event that lasted about 6 hours and didn't match the signature of a meteorite impact, suggesting it originated deep inside the planet. Mars lacks plate tectonics, so what causes these quakes is still uncertain. Internal stress buildup, thermal contraction, residual geological activity from a once far more active world. Recent studies have found evidence of at least 40 volcanic events, some only a few million years ago. The Noctis Labyrinthus region, a vast network of valleys and canyons near the Tharsis volcanic plateau, home to the solar system's largest volcano, Olympus Mons, shows evidence of volcanic activity having released water in the past, possibly creating the ancient river systems we see today. Then there's what humans are building toward Mars right now. The MOXIE experiment aboard Perseverance successfully produced oxygen from Mars's carbon dioxide atmosphere. This is not a trivial achievement. It's a demonstration that the chemistry works, that you can convert the gas making up 95% of the Martian atmosphere into breathable oxygen and, crucially, into rocket propellant. Scaled up, a version of this system could produce tens of tons of oxygen, enough for a crew's life support, and enough to fuel a rocket back to Earth, which would otherwise require launching hundreds of tons of propellant from Earth at astronomical cost. The ability to make oxygen from the Martian atmosphere is arguably the single most important enabling technology for human presence on Mars. And the helicopter. Ingenuity was designed as a technology demonstration. 5 flights, 30 days, proof that powered flight was possible in Mars's thin atmosphere. It flew 72 missions over more than 1,000 Martian days. It set range records. It survived dust storms and sensor failures and communication blackouts. Its final flight came in January 2024, when rotor blade damage grounded it permanently. But the lessons from Ingenuity are already being applied to the Dragonfly rotorcraft heading for Saturn's moon Titan, which will explore its surface from the air in ways no ground-based rover could manage. The helicopter opened a door. Mars is not a solved problem. It may be the most complex challenge humanity has ever set itself, but the obstacles are engineering obstacles, and humanity has a way with those. Now let's think bigger. Let's talk about what happens when a star dies. Because a supernova is not just an explosion, it's a cosmic forge. Every element heavier than iron, the gold in any jewelry you might be wearing, the iodine in your thyroid, the uranium in nuclear power plants, was created either in stellar interiors or in supernova explosions and scattered across space over billions of years, eventually incorporated into planets, oceans, and after a very long time, into you. We are, in a very literal chemical sense, made of exploded stars. That line is true, and understanding how those explosions work matters not just academically but in the most fundamental sense of understanding where we came from. The star everyone has been watching most closely is Betelgeuse, the red supergiant on Orion's shoulder. Betelgeuse is not just visible to the naked eye, it's one of the brightest stars in the night sky, about 700 light-years away, roughly 15 to 20 times the mass of our Sun. Its diameter is so enormous that if you placed it at the center of our solar system, its surface would extend roughly to the orbit of Jupiter. It is a monster, and it is, by stellar standards, very near the end of its life. In late 2019 and into 2020, Betelgeuse did something unexpected. It dimmed dramatically, more than astronomers had ever recorded, so dramatically that it dropped out of the top 20 brightest stars in the sky. The internet went somewhat wild. Astronomers were asked daily whether Betelgeuse was about to go supernova. Would it be visible in daylight? Would it affect Earth? The answer, as it turned out, was no. What happened, and this is actually a fascinating story in its own right, was a massive surface mass ejection of unusual scale. The material ejected from the surface cooled as it moved away and condensed into dust, forming a large cloud that obscured a portion of Betelgeuse's surface from our view. Two shock waves, one in 2018 and another in 2019, had disrupted the star's surface and created the conditions for this exceptional dimming event. Hubble imaging confirmed it, and observations at multiple wavelengths, infrared, microwave, radio, allowed scientists to see through the cloud and understand what had happened. What this tells us about Betelgeuse is genuinely interesting. Betelgeuse is an explosive, low-density plasma cloud of extraordinary dynamism. It changes shape. It pulsates on multiple cycles, periods of about 185 days, 230 days, 420 days, and 2200 days, each reflecting different internal processes. Simulations show its surface churning with convective cells so large that a single one would dwarf our entire solar system. The current scientific consensus is that Betelgeuse is not imminently going supernova. It has likely thousands to hundreds of thousands of years left, but when it does go, it will be visible from Earth in daylight. It will cast shadows at night. It will be one of the most extraordinary astronomical events in recorded human history. Speaking of extraordinary astronomical events, in October 2022, a gamma-ray burst was detected that earned the nickname BOAT, brightest of all time. Officially designated GRB 2210MO9A, its origin was a galaxy about 2.4 billion light-years away. That's nearly incomprehensibly far. And yet the burst was so energetic that it measurably affected Earth's ionosphere. Radio communications were disrupted. The ionization level of the atmosphere spiked. Satellites were temporarily blinded. From 2.4 billion light-years away, a dying star made itself felt on Earth in real time. The burst lasted about 7 minutes, much longer than typical gamma-ray bursts, suggesting it came from a massive, rapidly rotating star whose collapse created an extremely focused, narrowly beamed jet of energy aimed almost exactly toward Earth. Being in the path of that jet from that distance produced effects we measured in real time. Being within a few hundred light-years of such an event could be sterilizing. BOAT was studied with JWST and other instruments in the hope that it might provide clues about the origin of heavy elements, gold, platinum, uranium, that aren't produced in regular stellar fusion and were theorized to form either in supernova explosions or in neutron star mergers. What scientists found was a surprisingly faint supernova remnant relative to the power of the gamma-ray burst, and no clear evidence of heavy element production from this particular event. The mystery of exactly where the universe makes its heavy elements remains open. Every answer comes with new questions. That's the nature of this work. Type 1a supernovae, a completely different class, produced when a white dwarf in a binary system accretes enough matter from its companion to cross a critical mass threshold and explode, are actually some of the most important objects in cosmology. Their intrinsic brightness is known and predictable, which means you can determine their distance precisely by measuring how bright they appear from Earth. Using these so-called standard candles in the late 1990s, astronomers made one of the most startling discoveries in scientific history. The universe's expansion is not slowing down as gravity would suggest. It's accelerating. Something is pushing the universe apart faster and faster. That something has been named dark energy. It accounts for roughly 70% of the total energy content of the universe, and we have essentially no idea what it actually is. That discovery came from watching stars explode. Now let's talk about something hiding. Beyond Neptune, beyond the orbit of the last confirmed planet in our solar system, a handful of small icy bodies are behaving strangely. Their orbits are extreme, elongated, tilted, and they cluster in ways that nothing in our current model of the solar system can fully explain. Their orbits are aligned, They point in the same direction. They're tilted the same way. The probability that this is random chance has been calculated, debated, recalculated, debated again, and remains, depending on who's doing the statistics, somewhere between suspicious and compelling. In 2016, astronomers Mike Brown and Konstantin Batygin at Caltech published a paper arguing that the best explanation for this clustering is the gravitational influence of a large, undiscovered planet orbiting the Sun in a wide, elongated path far beyond Neptune. They called it Planet 9. Their model suggested it could be about 5 to 6 times the mass of Earth, orbiting at a distance somewhere between 400 and 800 astronomical units, roughly 10 to 20 times farther from the Sun than Neptune. At that distance, with that mass, it would never have been detected by any telescope survey conducted to date. Its orbit would take thousands of years to complete. It moves so slowly against the background sky that distinguishing its motion requires years of patient observation. And it would be so cold that it emits almost no infrared radiation, making thermal detection just as difficult. The idea that our solar system has a major planet we've never seen, that it's been there for 4 billion years and we simply haven't looked in the right place, is both humbling and genuinely plausible. The search is active. In a preprint from early 2024, Brown and Batygin reported results from an analysis of Pan-STARRS 1 survey data, one of the deepest sky surveys ever conducted. They searched through billions of detected objects and found nothing. But the non-detection excluded approximately 78% of the parameter space where Planet 9 could reside. The remaining 22% will be the territory of the Vera Rubin Observatory, currently being commissioned in Chile, which will survey those regions with significantly greater sensitivity in the coming years. And here's where the story gets even stranger. Some researchers have proposed that what we're calling Planet 9 might not be a planet at all. It might be a primordial black hole. A tiny black hole, perhaps the mass of Earth but no bigger than an apple, formed in the extreme density of the early universe shortly after the Big Bang. Such an object would be gravitationally identical to a rocky planet of the same mass. It would be essentially invisible to conventional telescopes. You could only detect it through its gravitational influence on nearby objects, which is exactly how we're searching for Planet 9 anyway. A primordial black hole lurking in the outer solar system would be one of the most extraordinary discoveries in the history of science and would provide direct evidence of exotic physics from the universe's first moments. Whether Planet 9 turns out to be a rocky world, a primordial black hole, a concentrated clump of dark matter, or nothing at all, the search for it is a reminder that our own backyard still holds secrets. From the edge of the solar system, let's travel inward to one of its most dramatic and well-studied residents, a world that humans have been gazing at in wonder since before written history. Let's talk about Pluto, because even though Pluto was demoted, it is anything but boring. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh at the Lowell Observatory in Flagstaff, Arizona, who was searching photographic plates for a moving object against the fixed background of stars, a painstaking process that required extraordinary patience. When he found it, the discovery made international headlines. The 9th planet, Pluto. It held that status for 76 years. Then the Kuiper Belt revealed itself in the 1990s, and it turned out that Pluto wasn't alone. It was one of the largest objects in a vast belt of icy bodies extending beyond Neptune's orbit. When objects like Eris were discovered that rivaled or surpassed Pluto in size, the International Astronomical Union was forced to confront the question of what exactly a planet is. In 2006, they voted. Pluto was reclassified as a dwarf planet, a decision that still generates heated debate and famously earned Neil deGrasse Tyson actual hate mail from elementary school children who felt personally betrayed. But whatever you call it, Pluto is extraordinary. And it wasn't until the New Horizons spacecraft flew past it in July 2015 that we finally saw it as something other than a blurry dot. New Horizons, a spacecraft roughly the size of a grand piano, launched in January 2006, covered more than 3 billion miles in just over 9 years, received a gravitational boost from Jupiter along the way, and arrived at Pluto moving at nearly 50,000 kilometers per hour. The flyby lasted only about 13 hours. In those 13 hours, New Horizons collected enough data to keep planetary scientists busy for over a decade. What it found was astonishing. Pluto has mountains, ice mountains made of water ice, which at Pluto's temperatures is as hard as rock and just as capable of forming dramatic topography. Some rival the Rockies in height. Pluto has nitrogen glaciers flowing slowly across its surface like ice glaciers on Earth. It has haze layers in its atmosphere that create a blue tint to its sky, the same scattering physics that makes Earth's sky blue, operating in Pluto's tenuous nitrogen atmosphere. It has active geology. It has seasonal changes. It has, in at least one spectacular region, evidence of possible cryovolcanism, eruptions of water ice slurry rather than molten rock. Sputnik Planitia is the crown jewel of Pluto's surface, the heart-shaped feature, about 650 miles across, that has become one of the most studied landforms in the outer solar system. It's a basin filled with nitrogen ice, its surface covered in convection cells, slow churning motions of ice driven by Pluto's internal heat, creating polygonal patterns each roughly the size of a country. This is not a frozen dead world. This is a world in slow motion, doing what planets do, moving, changing, driven by internal energy. The mass distribution in this basin hints at the possibility of a liquid water ocean beneath Pluto's icy crust, isolated, dark, but potentially liquid due to the antifreeze effect of ammonia and the pressure of the overlying ice. Pluto's largest moon, Charon, is nearly half the size of Pluto itself, so disproportionately large that the two objects orbit around a common center of gravity located in the space between them. This makes the Pluto-Charon system truly a binary dwarf planet. Charon has deep canyons, mountains, and its own complex geological history. Its north pole is coated in a reddish material called tholins, complex organic compounds formed when ultraviolet light breaks down methane that escaped from Pluto's atmosphere and settled on Charon's surface. The surfaces of these two worlds are chemically connected across the void between them. After its historic flyby of Pluto, New Horizons traveled onward to Arrokoth, a Kuiper Belt object it reached on January 1, 2019. Arrokoth looks like a reddish snowman, two lobes joined together, and it told an important story about how the early solar system worked. The large lobe is not a single formation, but a cluster of smaller rocks that merge gently together at speeds of less than a few feet per second, refuting the older notion that planetary formation involved violent high-speed collisions. The outer solar system, it turns out, built itself patiently, quietly, in a process more like slow settling than catastrophic impact. Now let's end where the view is most spectacular. At a planet that has been capturing human imagination since the moment anyone got a good look at it, Saturn. Galileo pointed his telescope at Saturn in 1610 and saw something he literally couldn't explain. He described it as a planet with ears. It wasn't until 1655 that Christian Huygens correctly identified those ears as a ring system. Nothing in astronomy had prepared anyone for that. A planet wearing rings. And here's a footnote that rarely gets enough attention. The Maori people of New Zealand, long before European contact, long before telescopes existed, apparently had mythology describing Saturn as having a belt, a parero, around it. How they knew this is genuinely unknown. The human eye cannot resolve Saturn's rings without optical aid. It's one of those historical mysteries that sits quietly at the intersection of indigenous astronomy and the question of how carefully pre-technological cultures observed the sky. Saturn's rings are mostly water ice, particles ranging from grains of sand to chunks the size of houses, all orbiting Saturn in a disk that's extraordinarily flat, yet extends hundreds of thousands of miles across. The Cassini spacecraft, which spent 13 years in orbit around Saturn before being deliberately plunged into its atmosphere in 2017, revealed the ring system in extraordinary detail. It found that the rings are surprisingly clean. Over 13 years, Cassini's dust analyzer collected only 163 particles from outside the Saturn system. If the rings had existed for billions of years, they would have accumulated far more cosmic dust from the interstellar medium. They haven't. The rings are young, only a few 100 million years old at most. Saturn itself is 4.6 billion years old. Its rings are a recent addition. What created them is still debated. The most likely scenario involves the tidal disruption of a large icy moon that wandered too close and was torn apart by gravitational forces. And those rings are disappearing. Ring rain, ring particles being drawn into Saturn's atmosphere by electromagnetic forces, is removing material at a rate equivalent to an Olympic swimming pool's worth of water every 30 minutes. At that rate, the rings could be gone within 100 million years. The planet that future civilizations will call Saturn, if there are future civilizations here to name it, might not have visible rings at all. What we're seeing right now, this extraordinary ringed planet that defined our image of Saturn since Galileo, is temporary. We are fortunate to exist at exactly the moment in the solar system's history when Saturn's rings are at their most magnificent. Saturn's North Pole hosts one of the most geometrically bizarre features in the solar system, a persistent hexagonal storm system that has existed for at least 4 decades of observation and possibly much longer. A 6-sided jet stream surrounding a central vortex, each side of the hexagon roughly the diameter of Earth. The winds inside reaching several hundred miles per hour. Laboratory experiments have reproduced hexagonal flow patterns in spinning fluids. The shape arises from wave patterns in fluid dynamics, but Saturn's hexagon extends thousands of kilometers deep into the atmosphere, far beyond any laboratory simulation. Every paper published about it seems to deepen the mystery rather than resolve it, and it has been sitting there rock solid and geometrically perfect for longer than we've been watching. Titan and Enceladus are two of the most exciting places in the solar system for the question of whether life could exist beyond Earth. Titan, Saturn's largest moon, has a thick nitrogen atmosphere rich in organic compounds, lakes and rivers and seas of liquid methane and ethane on its surface, and almost certainly a global subsurface ocean of liquid water kept from freezing by tidal heating. The surface processes on Titan are eerily similar to Earth's. There are drainage channels, deltas, seasonal changes in the sizes of the methane seas. Organic compounds rain down from Titan's thick orange haze layers continuously, making it a natural laboratory for the prebiotic chemistry that preceded life on Earth. NASA's Dragonfly mission, launching in the 2030s, will send a rotorcraft to fly across Titan's surface, covering distances in hours that would take a rover years, analyzing organic compounds and searching for signs of chemistry that could tell us how life begins. Enceladus is a different kind of miracle. It's a small, icy moon that should be cold, dark, and dead. Instead, its south polar region is covered in geysers erupting from fractures in the ice, launching plumes of water vapor, ice particles, and organic compounds hundreds of kilometers into space. The Cassini spacecraft flew through those plumes and analyzed their contents: water, sodium, silica nanoparticles consistent with hydrothermal vents, carbon dioxide, methane, and molecular hydrogen, which is a product of hot water reacting with rock. Beneath Enceladus's icy shell is a confirmed global liquid water ocean. At the bottom of that ocean, apparently, are hydrothermal vents, the same type of environment where some of the most extraordinary life on Earth thrives, in communities that don't need sunlight, that derive their energy entirely from chemistry. Life doesn't need the sun. It needs liquid water and an energy gradient. Enceladus apparently has both. The ocean is essentially mailing samples to space, free of charge, waiting for someone to fly through them with the right instruments. No such mission is currently approved. But the scientific community understands the opportunity. The argument is about budget and scheduling, not about whether it's worth doing. And so we come to the end of a journey that has taken us from the nearest star to the edge of the solar system and back, from the frozen south pole of the moon to the methane lakes of Titan, from the question of whether we can ever cross 4 light years to the question of whether life might already exist in an ocean we could reach within a century. What ties all of it together is the same thread that connects Gagarin to Betelgeuse to Chandrayaan-3 to that hexagonal storm on Saturn. The universe is stranger, larger, more detailed, and more alive with phenomena than any previous generation of human beings could have imagined. And with every instrument we build, every mission we fly, every dataset we analyze, we find that the strangeness deepens rather than resolves. Every answer comes with 3 new questions. Every confirmed discovery opens a door onto a corridor of new mysteries. There is a moment in the New Horizons story that stays with me. In 2015, as the spacecraft approached Pluto for the first time, the team at Johns Hopkins was receiving images that showed, for the first time, not a blurry dot but a world. Mountains, a glacier in the shape of a heart, a haze in the atmosphere, an active, complicated surface on a world that science had essentially written off as a frozen relic. The team broke down. Scientists wept, not because it was sentimental, but because the universe had just done what the universe always does when you finally look at it closely enough. It was so much more than anyone expected. That is the real story of space exploration. Not the rockets, not the funding battles or the engineering margins. The real story is that every time we look, we find more than we bargained for. Every planet is weirder than the models predicted. Every moon has something unexpected. Every galaxy observed in a new wavelength shows structures no one anticipated. The universe is not running out of surprises, And we are nowhere near running out of questions. The closest star to our sun may have a habitable world. There may be life right now in the ocean of an icy moon we could reach within our lifetimes. Something gravitationally strange is happening at the edge of the solar system. A star you can see with your naked eye tonight is slowly approaching the end of its life, and when it goes, it will be one of the most dramatic events visible from Earth in 1,000 years. The planet we thought was deep blue for 30 years is not actually blue, and there may be a black hole the size of a basketball drifting somewhere beyond Neptune, 8 billion miles from you, older than the solar system, patient and invisible and waiting to be found. The universe doesn't care whether we find any of this. It will go on expanding and cooling and cycling through its processes whether or not we're paying attention. But we are paying attention. And the fact that matter evolved, after billions of years into creatures capable of curiosity, might just be the most extraordinary thing in all of it. Keep looking up.